Hello, today I'm going to cover part 2 of section 6.1, solving systems by substitution. While effective, solving a system graphically can be tedious and limiting, especially when the solution has fractions or the lines are nearly parallel. Instead, we can solve a system of linear equations algebraically using a method called substitution. So example 5, solve the system of equations negative x plus y equals 3 and 3x plus y equals negative 1 by using substitution. So for this first example, I do have it laid out step by step to work through it. So step 1 is choose an equation and solve for the first variable in terms of the second variable. You get to choose which equation and you get to choose which variable is the first variable. So in this example, let's just choose the first equation. And let's choose the first variable to be y and the second variable to be x. Doesn't always have to be that way though. So I'm going to solve for y. So I add x. Y equals x plus 3. Step 2, substitute your solution from step 1 into the other equation. So that means into the equation you didn't pick. So we substitute y equals x plus 3. So since the equation we didn't pick was 3x plus y equals negative 1, and we're going to substitute y equals x plus 3, that means this y gets replaced by x plus 3. So we get 3x plus x plus 3 equals negative 1. Now this new equation only has one variable, so we know how to solve it. So I'm going to start off by combining like terms. 3x plus x is 4x. Plus 3 equals negative 1. Subtract 3. 4x equals negative 4. And divide by 4, divide by 4. We get x equals negative 1. Now remember, the solution to a system of equations has to be an ordered pair. So even though we got a solution for x, we still need to find what y is. So to figure out what y is you take the solution from step 2 and enter it into either equation, the original or the other. Again, this makes a linear equation with only one variable, so we get to solve that equation for the only variable it has. So let's put it into the first one. So the first one again was negative x plus y equals 3. And we plug negative 1 into there. So we get negative 1 plus y equals 3. Negative 1 is positive 1 plus y equals 3. Subtract 1, we get y equals 2. So now we have an ordered pair. Step 4 is to put the solutions from step 2 and 3 together as an ordered pair. This ordered pair is your solution. If desired, you can check both. So our final answer is negative 1, 2. Example 6. Solve the following system. So we're going to solve example 6 and 7 by substitution. So for example 6, I'm going to start off with the first equation again. So we get x minus 2y equals 8. This time though, I'm going to solve for x. If I try to solve for y, I would have to divide by 2, which might give me a fraction. If I solve for x, I don't divide by anything, so I shouldn't get any fractions. So that's why I'm choosing x. So I add 2y to both sides. We get x equals 2y plus 8. Now I substitute that in to the other equation. So the other equation is 3x minus 6y equals 24. So the x this time becomes 2y plus 8. So since this is 3 times x, I have to take 3 times this, the entire thing, so I need parentheses. Now I distribute the 3, we get 6y plus 24 minus 6y equals 24. Then 6y minus 6y cancels out, and we get 24 equals 24. Now this is a special case because I didn't get an answer for y. The y's ended up canceling out. When this happens, when the variable cancels out, you look at the statement that's left over. So we have 24 equals 24. You ask yourself, is this true? If yes, that means there are infinitely many solutions. So that means it's consistent and dependent. Now, sometimes you're still asked to come up with the solutions, because even though there's infinitely many of them, not every number is a solution. And what you do is you look at the equation you solved. Let me choose a different color. We look over here at this. So that tells me for my solution, which is an ordered pair, the x value is 2y plus 8. Or if this was solved for y, then your y value would be whatever this equation was. Just in this specific example, we solved for x. And then whichever one you didn't solve for is called a free variable, and it gets to be whatever it wants, so it gets to be y. So this is the general form of all the solutions. So to get a solution, you pick a value for y, that's your y value, plug it in over here to get your x value. Pick another value for y, get another x value, so on and so forth. And that's why there's infinitely many solutions. Okay, example 7. Okay, again, I'm going to start out with the, actually just to change things up, let's start with the second equation. So 6x minus 2y equals 10. And here, because the y has the smaller number in front of it, I'll solve for y. So subtract 6x, minus 2y equals negative 6x plus 10. Divide by negative 2, divide by negative 2. Y equals 3x minus 5. We then substitute this into the other equation. So we get 3x minus y equals 7. The y gets replaced by 3x minus 5. And then we get 3x minus that. So this is where you have to be careful. Because of this minus sign, that's why I need parentheses. In example 5, it was a plus sign, so I didn't need parentheses. So then we get 3x minus 3x plus 5. And that's why we need the parenthesis, because this negative sign has to get distributed. Now here, the 3x's cancel out, so everything cancels out again. So then we look at the statement that's left over. Is this true? If no, then there is no solution. Which means it's inconsistent and independent. And we don't have to find a general solution this time because there is no solution, so we're done. Okay. We say that a system like that in example 6 is dependent when the solution set is infinite. Graphically, this means we have the same line. Algebraically, we can see this by getting a tautology That's when you get a true statement. So we had 24 equals 24. You could get 0 equals 0, -3 equals -3, anything like that. You can also see it if you put them both in slope-intercept form first. Then if they match exactly, then it's also dependent. Or noticing that one equation is an exact scalar multiple of the other. This one works, but takes a little bit of ingenuity to get that one. So here, I gave the definition of what dependent is. If it's not this, then we call it independent. So when there's no solution or one solution, we say independent. We say a system like that in example 7 is inconsistent. When there is no solution at all. Graphically, this means we have parallel lines. Algebraically, we can see this by getting a contradiction, like 5 equals 7 in our example, or 0 equals 4 when we try to solve by substitution. Putting both lines in slope-intercept form, the slope will match, but the intercept won't. Or noticing that one equation is a scalar multiple of the other, except for the constant term. Again, that one takes a little bit more ingenuity than the other two. And just like how I gave you a definition of dependent and just said if it's not this, it's independent. Here's your definition of inconsistent. If it's not this, then it's consistent. So if there's one solution or infinitely many solutions, we say it's consistent. And that is it for section 6.1.